Last time we talked about limiting reagent, we talked about excess reagent, we talked about percent yield, and also about concentration. We mentioned about concentration, so we'll just practice more to understand what does all this mean. Um, so if you remember, we talked about anemia last time.
Excuse me.
Yeah,
It's Said. Excuse me for
yeah.
interrupting the class. Would you please to answer to all our questions whenever if we can we have any chance and time.
Which questions I can you just
Uh,
specify?
the first and second question. You know, the type of question is completely unfamiliar to my eyes, and also we have the time limitation. It's completely, uh, you know, uh, I cannot focus on the questions.
Yes, so you're talking about the quiz, right?
Yeah, quiz. Yeah.
Okay. So all right, so we can just discuss about the quiz.
Thank
Wait
you.
a
Thank
second. So these are quizzes, quick questions for quizzes, and can you specify which questions you are interested?
you. First and second better.
Okay, so this one and this one.
Yeah.
All right, so honestly, all these four questions are very much similar, very much similar. So if the third and fourth one was not a problem, so none of them can be the problem. Just maybe it's rewritten in a different way, but they are quite similar questions. All right, so let's just discuss about the first and the second one. So it says that no prescription pain relievers Advil and Luprin contain ibuprofen whose molecular weight, molar mass is already given. So if all the tablets in a bottle of pain reliever together contain this amount in moles of ibuprofen, what is the number of grams of ibuprofen in the bottle? All right, so what does it mean actually, this information? Can you say, tell me? what does it mean? So its molar mass says that it's 206.3 gram per mole. Okay, so you don't need to understand.
The molarity.
Okay, so you don't need to. So there is a question that there was a problem to understand this formula. You don't need to understand this formula at all, because only thing you need to find is that the mass of the ibuprofen you have in the bottle. That's the whole story, and you don't need to understand what is the structure of this formula, because we haven't studied any structures of organic molecules, so there's no requirement for that to understand what does it mean, this formula. Only thing you need to understand, what does it mean molar mass? This is what you need to know. Can somebody tell me what is the molar mass? Oh, okay, so let me just finish this one. So this means that you have in 1 mole of ibuprofen weighs 206 grams. This is what does it mean. Okay. So then it says that what's gonna be the number of grams of ibuprofen in the bottle. So basically, you want to find the mass of ibuprofen in the bottle. And we know also that we have this amount in the bottle. So it means that we have 0.082 moles in the bottle. So it's going to be X. So you need to find X. This is the whole story. Can you find X here?
Doctor, you know what was the problem?
Doctor, we want molar mass.
So that's the molar mass over here.
This is a completely simple question, but the structures and the face of question completely mislead all of us, I think.
Okay, so I mean,
So this is
I
completely easy question. Thank you.
this is very easy question, absolutely easy question. Only thing you need to realize only this one. It takes
Yeah,
only 1 minute.
yeah, exactly.
Yeah. Is
So
it clear now?
yeah, of course. Thank you.
Yeah. So then it says the next one, how many molecules of ascorbic acid, vitamin C6H8O6 are in 500 milligram of tablet, right? Is this the second question was the problem?
Would you please describe this question?
The second
The first
one.
one. Yeah, thank
Okay, so
Doctor,
yeah.
we changed from grams to moles, and then we changed from moles to molecules. Is it right?
So first of all, you change it to grams. For example, it's going to be 0.5 grams.
Grams, yeah.
Yeah, this is what is already given. And now you need to find how many molecules of ascorbic acid you have in 0.5 gram of vitamin C. They're the same thing as ascorbic acid, okay? So what you need to do is that to find molecular weight of this molecule.
Doctor, you must find Avogadro's number.
We do not need to find Avogadro's number is already known. It's 6.022. So this is Avogadro's number. It's already known. This is a constant. We don't need to find it. It's already known. So that's the Avogadro's number.
Multiply moles. We must find the moles.
Then you need to find molar mass of this. This is what you need to find. Okay, so you need to add 6 times 12. It says over here, so it's 12 gram per mole, right? Plus 8 plus 6 times 16. This is what you need to find. So just calculate this one. Whatever it is, that's the amount of Avogadro's number of molecules. Okay, whatever it is, I don't know, let's call it A. And once you know what is A, so you can find in 0.5 grams is going to be X, number of molecules. This is it. This is another 2-3 minutes. Okay. Is it clear?
Yes, doctor, yes.
Okay. Any other questions about this quiz? And the rest is the same, basically. The approach are the same. So we just we need to know what is the relationship between these 4 parameters: mass, molar mass, moles, and Avogadro's number. Okay, so let's just if you have questions, just either ask it, or you can just send it through the chat or anything like that. All right, so let's just continue with the class we started.
Doctor,
Yeah, I think it's on the same.
last week we stopped in the end of lecture 2. We didn't finish it.
Oh, let me see. Okay, so let me see what was the last time. Yeah, we just yeah, so let's just okay, so let's just finish this one because we already talked about anemia, right? So we talked about, okay, let me share this one with you. So we talked about anemia. So this is what I'm saying, that since we talked about anemia, I wanted to just continue about that. But so we talked about this part, right? So we talked about, this is what we talked about last time, right? So this is, we stopped over here, right? All right, so let us finish this one, and then I'll go to the practical stuff if you like that. Okay, so let's continue from here. So just to remind you, it was about solubility of gases and salts, for example. And we have completely different situation. If we have gases at high temperature, the solubility drops. So we have high temperature and solubility drops. So this is solubility over here, and this is temperature. So if you compare, for example, for oxygen, so which is green line, so this is oxygen, solubility of oxygen depending on temperature. So you can see that, for example, at 10 degrees Celsius, the solubility is about 5.5 milligrams per 100 gram of water, but at 30 degree, it's about 3.8, it's over here, of milligrams of oxygen per 100 gram of water. So solubility at increasing the temperature drops. So it means that if you have cold water, you can expect that the oxygen in there is more than in hot water, right? It's obvious when you boil the water, you can see all kind of bubbles are coming out. The opposite is for solids, salts, and for example, sugar. And you know for sure that if you have hot water, you can dissolve sugar better than if you have cold water, for example, at 0 degree or 20 degree, right? So at 0 degree, it's ice, but at 20 degree, for example, the solubility of sugar is less than solubility of sugar at 60 degrees. So it's over here. So this is how it's related to the temperature. Another thing is gases. The solubility of gases depending on pressure. So if you have high pressure, you can dissolve gases more, of course, in water. And this is how, for example, Coke is made or any other beverages like soda drinking, because you need to dissolve carbon dioxide in there. And for that, you need high pressure. So this is how you're doing that you're just making pressure inside the, say, chamber or say bottle or can or anything. Or at the end, at some point, this pressure is equalized inside the, there is some kind of equilibrium conditions inside the solutions and on top of solution. And there is an equilibrium, so you cannot make a solute to be dissolved more. So there is some equilibrium established. There's the evidence that once you open the Coke, so all this carbon dioxide escapes, right? And it's just fizzing and bubbling and stuff like this. So this is why, because once you open the can, the pressure inside drops. And once it drops, the solubility decreases, and all carbon dioxide, not all, but many of those molecules escape from the can. So we also, there was also information about electrolytes. Yes, so you guys know that if you dissolve salt in water, it becomes electrolytes. For example, our body fluid is electrolyte because we have sodium, potassium, and chloride ions in our body fluid, and also in blood. Also, we have some ions, right? So all these are electrolytes. What is electrolyte? These are compounds which can be broken down in ions. So basically, they can be charged after dissolving in water. So, for example, sodium is plus charge, chloride is minus charge. So as much you have this electrolyte, you can have more conduction of electricity, for example, in that. Well, about precipitation and solubility, this is also related to solubility. So there is a point when you cannot dissolve more compounds in a solvent. And how it can be reflected in terms of, say, medicine is that it might deposit, for example, sodium urate. Sodium urate can be precipitated in the organism because of dropping of solubility of that in the organism. Why? Because it cannot be extracted efficiently, so then it precipitates. And by the way, the gout is related to the precipitation of this sodium urate. One more thing I want you to pay attention. I want you to look at these molecular equations, ionic equations, and net ionic equations. So this is the molecular equation over here. And it shows that at the beginning we take barium chloride, which is aqueous, which means that it's soluble, so it's dissolved. We also add sodium sulfate, also dissolved form of sodium sulfate. Basically, this is a solution. You can mix these two in solution. And as a result, you make barium sulfate, which says over here S, which means solid. Okay, So it means solid. And then also we can make sodium chloride, which says aqueous. So it means that it stays in solution as a dissolved form. But barium sulfate is a solid, and this is how it looks like after precipitation. So it precipitates out of solution. So that's the molecular equation over here. This one is molecular equation. So what is ionic equation? So ionic equation tells us how we break down, if we can break down each of these compounds in ions. For example, the first one can be broken down like this: barium 2 plus aqueous plus 2Cl minus aqueous plus 2N, I'm sorry, this should be plus over here. This is wrong. This should be plus. Na plus, right, plus SO4 2 minus. All of these are dissolved and they are broken down in ions. So because we have these oxidation states, right, charges over here. So it means that they are ions. Okay. But if we go next, the left and right hand side from the arrow, so we can see that barium sulfate is not broken down in ions. Why? Because it says it's solid and precipitated. It cannot be like dissolved in water. It doesn't dissolve in water. Barium sulfate doesn't dissolve in water. Unlike, say, sodium chloride or barium chloride or sodium sulfate, you can put those salts in water, they will dissolve, but barium sulfate will not dissolve in water. It's not soluble. So then it means that you cannot break down this in terms of ions. And then, but sodium chloride, again, it should be plus over here. This is mistake. So sodium plus and chloride minus. Okay, you can just, and then that's the ionic equation. So this is ionic equation. And the rest one is the net ionic equation. What does it mean is that we look at the left-hand side of ionic equation and the right-hand side of ionic equation, and we cancel out each and every identical ions. So for example, from left-hand side and the right-hand side, we have identical ions, sodium, sodium, chloride and chloride, right? And what we're left with is barium ion 2 plus and sodium and sulfate, I'm sorry, sulfate 2 minus. And it creates barium sulfate solid. So that's the net ionic equation. So why we need to know that? It's to identify which species in the solution create a product. Others might be spectator ions, but the product can be created by like barium sulfate, and which can precipitate, for example. So we kind of identify the mode and the form of existence of ions in solution. We'll need this kind of approach when we'll start some colligative properties and osmosis dialysis. So it can be
Doctor,
useful. Yeah.
should we memorize those one, or just know
So
the
you need
different
to understand how to go from molecular equation to ionic equation, from ionic equation to net ionic equation. So
Okay.
to memorize this, you can find it out because you need to memorize what is the oxidation state for sodium. Yes, because it's only 1 plus. It cannot be 2 plus, 3 plus, or anything. So it's +1. For chloride, in sodium chloride, you need to know that for sodium it's 1 plus and for chloride it's 1 minus. If you know this, you can easily identify what's going to be the oxidation state for barium, because you see that it's with 2 chlorines over here. So overall chlorine is here is 2 minus, right? So we have one minus plus the other one minus. So overall it's 2 minus. So this 2 minus needs to be balanced by the counter ion, which should have the same amount overall charge, which means that it's going to be 2 plus, because you have 2 minuses over here. So it's going to be 2 plus. This is why you have 2 plus over here. The same thing about sulfate ion. So you can see that this is with 2 Na plus, right? Overall, we have 2 plus over here, so it's going to be 2 minus over here. So needs to be balanced. All molecular equations needs to be balanced in terms of charge.
Okay.
So here we have acid-base neutralization reaction. So we know that if we add acid to base, we will make salt and water. So what is acid and base? So this is acid, sodium, so HCl is acid, hydrochloric acid, right? And this is the base, sodium hydroxide. This is the base. This is the salt, right? So this is the table salt, this is just water. Okay, so we need to know we have acid plus base, we always make salt and water. This is why it's called neutralization reaction, because we neutralize acid properties and base properties of initial reagents. And basically we make very comparably harmless salt, which we eat every day, and just water, which is also harmless, right? But at the beginning we had very dangerous and corrosive HCl and dangerous NaOH. These are very strong base and acid, respectively. Okay. Also, we have some oxidation reduction reactions when we oxidize one species with, so for example, oxygen usually is used as an oxidizer. So it oxidizes other elements. For example, iron is rusted because of effect of oxygen. So oxygen oxidizes iron, and this kind of reaction, sorry, it's a redox reaction. This is just examples of redox reactions. For example, rusting, corrosion, it's redox reaction. For example, combustion, this is combustion reaction, right? Reacting with oxygen, that's the combustion reaction. That's the redox reaction, because here we can think that, you know, carbon can be partially, not really oxidized, but it creates partial positive charge on it. Respiration is redox reaction. Bleaching, by the way, it's redox reaction using peroxides. And in metallurgy also we have many redox reactions. I'll not stop too much here, so it just shows that what is the activity series of different ions against, say, hydrogen. And it shows that which element can substitute hydrogen in water. For example, you have water, right? H2OH, that's the same as H2O, it's the same thing, okay? So you have this, right? So if you add a lithium, definitely it will kick out one of the hydrogens and will take a place in there. Or if you add Na, it's vigorously reacts with the water very, very actively. It's very dangerous to put sodium, just sodium, piece of pure sodium in water. It reacts vigorously. So this is what shows you that. Okay, all these elements are very actively react with water. So others are less reactive with water, and the rest are basically, these are almost unreactive with water. Okay, so why this gold and platinum and silver are very stable against water? So they cannot be corroded because of their activity series, the position in activity series. This is why gold is such a precious metal, so it cannot be oxidized, not only because of the color and nice outlook. It cannot be oxidized, okay? It's like it cannot be degraded in air, in some other conditions. The platinum is the same, so they are noble metals, so they don't react with water. Okay, so we have some more oxidation redox reactions. So we already kind of discussed about this one. Yeah, so this is what is very important also we need to discuss. And our next quiz will be based on this concentration of solution, so this issue. I have, yeah, so we talked about moles, right? We talked about molar mass, we talked about mass in grams, right? But we never specified in what amount of solvent we have this number of moles. Say, we always say that, say we take 1.5 moles of, say, sodium chloride, right? And we can find what is this in mass. So what's going to be the mass of 1.5 moles of sodium chloride? But we never say, we have never said before in what kind of amount of water we want to dissolve this 1.5 moles of sodium chloride. So if we don't specify that, we never know what is the concentration. But if we specify that I want to take 1.5 moles of sodium chloride and I want to dissolve it in 1 liter of water or whatever amount of water, then I can understand and I can find what's going to be the concentration of sodium chloride in solution. Okay. If the same thing is, for example, the concentration of, say, our class right now, like online class, right? The concentration of our class is 25 people per class. Okay, this is very important to mention. What is the environment you have this amount of people? If you just say that, okay, we are 25 people, it's not gonna be the amount, it's not gonna be the concentration of people, okay? But if we say that we are 25 people per class, then it means that we know the concentration of people in particular environment, all right? If we consider the class as an environment. The same thing about chemicals. So if we specify in what amount it is dissolved or in what amount it exists, then we know what is the concentration. So the unit for concentration is moles per liter, and that one is called molarity. Okay, so which means that we know moles, we know the volume. So we have moles per volume, and if we specify volume, which is in liters, so we can say that we have moles per liter. All right. Another unit for concentration can be weight volume percent. For example, we take something in grams. Instead of moles, we take something in grams. For example, I don't know, 2 grams. And if we specify in what kind of amount of volume we have, we can calculate volume or weight volume percent. Also, we can say volume percent. What does it mean is that if we mix two different solutions, say if we mix ethanol and water, right? So if we mix ethanol and water, say if we take 3 milliliters of ethanol and we dissolve it in 1 liter of, or in 100 milliliter of water, then we can find the volume percent concentration. And the one more is parts per million. Parts per million, or called ppm. This is the parts per 10 in power 6 parts of environment. For example, it's very often used to characterize the air pollution, the solid particles in air. So say if there is 1 particle per 1 million of molecules of oxygen, for example, in air, right? So we can say that the concentration of this solid particle which flows around in air is going to be 1 per million, which is ppm. So it's going to be 1 ppm. Okay. How to find all these concentrations? So molarity we can find just divided moles of solute, liters of solution. So say if we have 0.1 moles of NaCl, and we have this one in 0.5 liters of solution. You can just divide 0.1 by 0.5, and that's going to be the concentration of table salt in water. Okay. All right. So then how to find the weight volume percent concentration? So you take the mass of solute, you take the volume of solution, and just you multiply by 100%. The percent volume percent concentration. You take the volume of solute, you take volume of solution, and you multiply it by 100%.
Doctor,
Yeah.
can you repeat the last thing?
Which one? This one?
Yes.
Okay, so if you want to find the percent concentration, you take mass of solute, say this is like 3 grams, right? And you take volume of solution, which say, I don't know, 500 milliliter, which is the same as 0.5 liters. And you divide these 3 grams by 0.5, and then you multiply by 100%. That's going to be the weight volume concentration. Okay. The same kind of approach is for volume percent concentration. You take the amount of solute in volume, amount of solution in volume, and multiply by 100%. I have less than 1 minute, but please come back once this 1 minute is off. So about the parts per million, it's mass of solute over mass of solution multiplied by 10 in power 6. This is called ppm, or you can take it in terms of volume. And also we have ppb, which is parts per billion. So it means that you need to think about 10 in power 9. So